Hello everybody. So today we will be starting with the fifth module, that is water chemistry. In water chemistry we will be discussing one important property of water, that is hardness. So what is hardness? You might have studied in your lower classes that hardness is defined as the characteristic property of water which prevents it from lathering with soap. That is a total hardness. Okay, why I have used the word total I will explain later, because we have a classification for hardness. So hardness of water or total hardness is defined as the characteristic property which prevents it from lathering with soap. Why hardness? Why does water show hardness? That is because of the presence of dissolved salts of calcium, magnesium, etc. So always remember, it is dissolved salt. Okay, dissolved salt of calcium, magnesium. So when the salt dissolves, you will get ions. So calcium, magnesium ions will be there, and some anions will be there: carbonate, bicarbonate, sulfate, or chloride. These are the anions that are present. So calcium and magnesium are the cations, carbonates, bicarbonates, sulfates, chlorides, these are the anions. Okay. So one important university question: what is hardness? What is its cause? Okay, this is a very important university question, so you have to answer this much. What is hardness? Definition. This is a definition, and this is the reason for hardness. Excuse me. Then why hardness is caused? Why hardness? So what happens when calcium and magnesium ions or salts are present in water? This calcium or magnesium will replace sodium or potassium in soap. Okay, so I'll show you the reaction. This is a reaction that takes place. This is soap, sodium stearate. This is soap. Soap is sodium salt of fatty acid. Fatty acid means a long chain carboxylic acid. So when this soap reacts with, let us say, magnesium chloride, so the sodium will be removed and magnesium will come and sit here. You get magnesium stearate, that is insoluble. Okay, that is insoluble, and it will precipitate out. Similarly, if calcium is present, calcium chloride or calcium salts are present, this calcium will come and sit here. It will form calcium stearate. That is also insoluble. It will precipitate out. So it will not form a foam. It will not lather. Instead, it will form a precipitate, or that is called as scum. SCUM, scum. This is another important question. Explain the principle chemistry behind soap not forming lather with water. Okay, this is another important question for a university exam. Now, let us classify water into two types based on hardness. Okay, you have hard water and soft water. What is hard water? Water which does not produce lather. Soft water, water which lathers easily. Okay. Hard water contains dissolved minerals like calcium and magnesium salt, but soft water does not contain these salts. Hard water causes high boiling point. The boiling point of water increases. If dissolved salts are present, the boiling point will not be 100, it will be much higher. And so in an industry, if you look, if you want to produce steam, you produce it by boiling water. So you require higher, more fuel, and you require more time. Okay, so higher consumption of fuel and time in the industry. It is a negative aspect as far as the industry is concerned. Whereas soft water, normal boiling point, so normal consumption of fuel and time. Soap cannot be used as a cleaning agent for hard water. Soap can be used as a cleaning agent for soft water. So these are some important points of comparison. Again comes your next question, university question: differentiate between hard water and soft water. So any 3 points at least you have to study. What are the disadvantages of hard water? Okay, so we can divide it into two parts. One is industrial disadvantage and the other is domestic disadvantage. Industrially, what are the disadvantages? We cannot use this in the dyeing industry. Okay, because dyes will not dissolve properly in this hard water. They will precipitate out because of the presence of magnesium and calcium ions. Then boiler corrosion. It corrodes the boiler. Okay, scale and sludge formation. What is the scale and sludge? Inside the boiler, deposits are formed. Deposits of the salt will be formed inside the boiler. That is scale and sludge, and that leads to corrosion. Another phenomenon is priming and foaming. Now, what happens is when you are generating steam, along with the steam, some salt will also go. Okay, into the gaseous state, some salt will also be there. That salt will deposit in the machines and it will corrode those machines. So that is called priming and foaming. So these are the important industrial disadvantages of hard water. Now coming to the domestic disadvantages, you may be knowing that first we cannot use soap. Okay, we cannot use soap with hard water. Second thing, it is not suitable for bathing. When the hardness is very high, it will cause some skin problems, hair problems, etc. and form stains on floors, basins or tiles. And it has a bitter taste at extreme level. So these are some of the important domestic disadvantages of hard water. Again, another question for the university exam. What are the disadvantages of hard water? Can be asked for 3 marks, can be asked for 4 marks also. So generally you have to study at least 4 points, 2 industrial and 2 domestic points. That is better always. 2 industrial points and 2 domestic points. Hardness can be classified into 2 parts. One is called permanent hardness, the other is called temporary hardness. Okay, so permanent and temporary hardness. Temporary hardness means it can be removed on boiling. Simple method like boiling will remove this temporary hardness. Permanent hardness, it is not removed on boiling. It will remain there even if you boil. Okay, you may be aware of this fact, temporary and permanent hardness. Now, why? Why can temporary hardness, or what causes temporary hardness? Or what causes permanent hardness? Now we have seen that hardness is caused due to calcium and magnesium salts. Actually, it is the calcium and magnesium ion which is causing the hardness. Here, temporary and permanent hardness is caused due to the anions. So if bicarbonate anion is present, that will cause temporary hardness, whereas other anions, sulfates, chlorides, etc., they will cause permanent hardness. Okay, so bicarbonate anion causes temporary hardness. Sulfates, chlorides or other anions, they will cause permanent hardness. Now there is another name given for permanent and temporary hardness. Temporary hardness is generally called as carbonate hardness. The permanent hardness is called non-carbonate hardness. Okay, this is a commercial naming. This is not an IUPAC approved naming. IUPAC approved is temporary and permanent. Commercially, it is called carbonate hardness and non-carbonate hardness. Okay, total hardness is equal to permanent hardness plus temporary hardness. Always, total hardness will be permanent hardness plus temporary hardness. So this is a very important thing. You have to always remember that total hardness is equal to permanent hardness plus temporary hardness. Next question. Differentiate between temporary and permanent hardness. Generally, it is asked for a 3-mark question. You have to give 3 points. Okay, 3 points you have to specify. Same question can be reworded. Differentiate between carbonate and non-carbonate hardness. The answer is the same. Okay, only thing the wording is different. Answer will be the same. Removal of temporary hardness. How can we remove temporary hardness? We have seen we can remove temporary hardness by boiling. Okay, now what happens on boiling? That is what we are going to see. What is the chemistry behind removal of temporary hardness by boiling? On boiling, carbonates and hydroxides will precipitate out and they can be filtered. Okay, you can filter and you can remove it. For example, if you take calcium bicarbonate, water sample containing calcium bicarbonate, if you boil it, what happens is calcium carbonate will precipitate out. You can filter it out. Similarly, if magnesium bicarbonate is present, so temporary hardness is caused due to bicarbonate ions. So if magnesium bicarbonate is present, it will precipitate out as magnesium hydroxide and we can filter and remove that. So this is the chemistry behind removal of temporary hardness by boiling. That is your next question. Explain the chemistry behind removal of temporary hardness by boiling. So this is the answer. On boiling, carbonates and hydroxides precipitate out and it can be filtered, and you have to give these reactions also. Now, how do we express hardness? Okay, so for expressing hardness, actually if you take different salts, like for example, you have magnesium chloride, you have a particular concentration of magnesium chloride in water, you have a particular concentration of another compound, let us say calcium sulfate in water. So the hardness should be expressed in a common way. Okay, you cannot explain or you cannot express hardness as concentration of the salt that is present. So what is done is a standard compound is taken. Here the standard compound is calcium carbonate. Okay, and hardness is converted into equivalence of calcium carbonate. So suppose magnesium chloride is the salt in hard water. Then the concentration of that magnesium chloride is converted into in terms of calcium carbonate. Okay. Suppose calcium sulfate is a dissolved salt in hard water. Then the concentration of that calcium sulfate is converted into equivalence of calcium carbonate. Okay. Now the question comes, why have we selected this calcium carbonate as a standard? Okay, so calcium carbonate has some features, some plus points. What are these plus points? It is the most insoluble substance formed in water treatment. Okay, most insoluble substance. Second, its molar mass is 100. That makes calculations easy because you may have to divide with 100, you may have to multiply with 100, so that is very easy. Whereas if you have to divide or multiply with another number like 134, that will be a little bit difficult. Okay, so these are the most important reasons why calcium carbonate is taken as a standard. So this is one another question, why is calcium carbonate taken as a standard in expressing hardness? This is another important university question. Now coming on to the calculation part, how will we convert the concentration of a dissolved salt in water to calcium carbonate terms, calcium carbonate equivalence? So suppose that you have a hardness producing substance. It is called HPS, hardness producing substance. It's a salt like magnesium chloride, calcium sulfate, or anything else. We want to find out the calcium carbonate equivalence of this hardness producing substance. Then the formula, suppose that M is the mass of the hardness producing substance in milligram per liter. Small m is the mass or the concentration of the hardness producing substance, and capital M is the molar mass of this hardness producing substance. Okay, 100 is the molar mass of calcium carbonate. NHPS is the valency of the hardness producing substance, and 2 is the valency of calcium carbonate. Okay, calcium carbonate, calcium has a valency 2, carbonate also has a valency 2. We will only look at the valency of the cation. Okay, valency of the cation is taken here. So small m is a mass or the concentration of the hardness producing substance in milligram per liter. Capital M is the molar mass of the hardness producing substance. 100 is the molar mass of calcium carbonate. NHPS is the valency of the hardness producing substance. 2 is the valency of calcium carbonate. So in that case, the hardness of that solution will be calculated, can be calculated using this expression. Hardness is equal to small m into 100 by capital M into NHPS by 2. Okay, hardness is equal to small m into 100 by capital M into NHPS by 2. So once you substitute the value of small m and capital M and NHPS here, we will get the calcium carbonate equivalent of that particular salt. Okay, calcium carbonate equivalent of that particular salt. So this is the calculation step. Units. What are the units of hardness? Several units are there. One unit is milligram per liter. Another unit is ppm. Yet another unit is degree Clark. Another unit is degree French. These are the four different units for hardness. Milligram per liter is the standard unit, SI unit. ppm is the commercial unit. Commercially, hardness is reported in ppm, and the relationship between milligram per liter and ppm is both are equal. 1 milligram per liter is equal to 1 ppm. So even if you use milligram per liter or even if you use ppm, it is the same, but generally hardness is expressed in ppm. Estimation of hardness. How can we estimate hardness? So we have seen what is hardness, what are its properties, what is the classification, how we can find out the hardness of a given solution. All that we have seen. Next thing is how we can estimate hardness. Okay, you are given a hard water solution. You want to find out what is hardness. You are not given any other data. So how can we find out the hardness? It is a very simple titration method. Okay, and that titration method uses this compound, that is EDTA, ethylene diamine tetraacetic acid. So this is your compound. Okay, ethylene diamine tetraacetic acid. Now in this compound I have marked some atoms as red color or in red color. Okay, why that I have done, I will be explaining. So what is this ethylene diamine tetraacetic acid? It is a compound which can form a complex with metals. Okay, this is a ligand. It is called as a ligand. You might have studied from the lower classes. So this ligand will form a complex with metal ions. Which all metal ions? Calcium, magnesium, or any heavy metal. It will form a complex. And the important thing is that it forms a complex in the 1:1 ratio. So 1 EDTA complexes with 1 metal. Okay. The complex is stable in basic pH. So if you provide a basic medium, this complex will be stable. The pH should be around 10. The indicator that is used, now here we are using it's a titration method. So when you are titrating, you need an indicator, and that indicator used here is called eriochrome black T. Short form is EBT. This indicator is blue in color. Okay, so EDTA forms a complex with metal ions in the ratio 1:1. The complex is stable in basic pH. What we are doing is we are taking EDTA in a burette. We are taking the hard water in a conical flask. We are titrating that. It's a titration method. So for titration, we require an indicator. That indicator is EBT. This indicator has a blue color. EBT forms an unstable complex with metal ions. Okay. So EBT also forms a complex with metal ions. EDTA also forms a complex with metal ions. But the issue here is EBT forms an unstable complex, but EDTA forms a stable complex. So we can utilize this for the titration. Okay, this fact will be utilizing for the titration. And when EBT forms a complex, the color of that complex is wine red in basic solutions. Okay, complex is wine red in basic solutions. Now, let us see that. Let us see what happens. You have this EBT complex, you have the metal ion. So once you add the EBT complex to hard water solution, this metal ion will form complex with the EBT. Sorry, EBT you are adding to the hard water, so the metal forms a complex with the EBT, and that is wine red in color. Now, EDTA metal complex is more stable than EBT metal complex. Okay, EDTA metal complex is more stable than the indicator metal complex. So, suppose you are titrating with EDTA. When you add EDTA, what will happen? This EDTA will take away this metal from this EBT. Okay, EDTA will take away this metal from EDT. When added to a solution, EDTA displaces EBT and forms a complex with the metal ions. Okay, so when it gets displaced, what will happen? You can see that EDTA is coming, it forms a complex with the metal ions, and this EBT fellow, it is sitting alone without any friend. Okay, it had a friend, the friend went to EDTA, so it is sitting alone. When it sits alone, its color is blue. Okay, when it sits alone, its color is blue. At the end point, free EBT is released into the solution, you get a blue color. Okay, so that is the end point. Change in end point is from wine red to blue. So if this is wine red, after titration, you get a blue color. Wine red to blue. This basic pH is maintained using ammonium hydroxide, ammonium chloride buffer. Okay, that gives a pH of 10. So basic pH is maintained using ammonium hydroxide, ammonium chloride buffer. Okay, this is the principle behind estimation of hardness using EDTA. So this is one important question. Describe the principle of estimation of hardness using EDTA. It's a very important question for your examination. So that is a principle. Now how can we practically do it? Another important question, what is the role of ammonium hydroxide, ammonium chloride buffer in the estimation of hardness using EDTA? So ammonium hydroxide, ammonium chloride buffer provides a pH 10. In that pH, what happens? EDTA forms a stable complex and EBT forms a wine red color. That is important. EBT indicator forms a wine red complex with the metal, and the EDTA forms a more stable complex with the metal. That is the important point. Okay. Quantitative estimation. Practically, how can you do this? So there are some calculation part also for this. The quantitative estimation is divided into 5 parts. Okay, there are 5 parts for this estimation. First part is preparation of standard hard water. Now I will explain what is that. Second one is standardization of EDTA. Third one is estimation of total hardness. Fourth one is estimation of permanent hardness. And the fifth one is estimation of temporary hardness. Okay. Now coming to the first step, preparation of standard hard water. What is this standard hard water? Why we are preparing that? And what is the standardization of EDTA? So EDTA solution, EDTA is a secondary standard. So its concentration should be fixed first, or it should be found out. Okay, you cannot directly get the concentration. We have to find out the concentration of EDTA. For that, we require a standard solution, that is standard hard water. Okay, what is the standard hard water? Very simple thing. Standard hard water is nothing but standard calcium carbonate solution. Okay, standard calcium carbonate solution. Whenever you use this word standard, it means of exact concentration. Okay, we know what is the exact concentration. For this, what is done? Solid calcium carbonate is dissolved in hydrochloric acid and diluted to the required volume. We will get standard hard water. Suppose you want to prepare 1 liter of standard hard water. Take some calcium carbonate, find out the correct weight, dissolve it in hydrochloric acid because it is not soluble in water. Dissolve it in hydrochloric acid, dilute to 1 liter. You will get the standard hard water. Okay. Now, if W milligrams of calcium carbonate is dissolved and made up to VMN or diluted to VMN, then the concentration of this calcium carbonate solution is obtained like this. C standard is equal to W by V, small w by small v. The unit is milligram per ml. So this is the concentration of the standard hard water. This is important. This has to be noted down because this will be used in the calculation part. So that is the first step. First step is over. Preparation of standard hard water. Second step, standardization of EDTA. How will we standardize EDTA? We have to do the titration. Okay. So we are finding out C EDTA, concentration of EDTA in this step. Standardization of EDTA means we are finding out the concentration of EDTA. Standard hard water is taken in a conical flask and mixed with ammonia buffer and indicator, EBT indicator. So this standard solution, hard water, a fixed volume, is taken in a conical flask mixed with ammonia buffer and indicator. We get a wine red color. It is titrated with EDTA taken in the burette. To take EDTA in the burette, to titrate with that, end point is change of color from wine red to blue. Okay, so color will change from wine red to blue. That is the end point. Note down how much volume of EDTA is required. Okay, so you know the volume of standard hard water taken. You know the concentration of standard hard water taken. You know how much volume of EDTA is used up for this titration. From that, we can find out the concentration of EDTA. Concentration of EDTA is given as C standard into V standard by V EDTA. Okay. V standard is the volume of standard hard water used. That we know, we have taken that, we have taken a fixed volume. Volume of EDTA required for the titration, that we can get from the burette reading. So C standard we have calculated in the first step. So substitute here, C EDTA is equal to C standard into V standard divided by V EDTA. You will get the concentration of EDTA. That is the second step. Okay, the second step is over. Now third step, total hardness. You have to find out the total hardness. What you do? You have to calculate this term C sample. You are given a water sample. Okay, you are given a water sample. You have to find out the total hardness of this water sample. So what will you do? You have already done the first two steps. You found out C EDTA. You know what is the concentration of the EDTA. Then what will you do? Hard water sample is taken in a conical flask and mixed with ammonia buffer and indicator. You take a fixed volume. A fixed volume of this hard water sample is taken, mixed with ammonia buffer, add the indicator, titrate with EDTA taken in the burette. End point is change of color from wine red to blue. Okay, so you repeat the same titration using hard water sample. We did it with standard hard water. Now repeat the same thing with hard water sample. Okay, so suppose the volume of the hard water sample taken is V sample and volume of EDTA obtained is V EDTA. C EDTA we have calculated from the second step. Substitute these, find out the concentration of the hard water sample. C sample is equal to C EDTA into V EDTA divided by V sample. Okay, C sample is equal to C EDTA into V EDTA divided by V sample. Once we get C sample, we can find out the total hardness. Total hardness will be C sample into 1000. Unit is ppm. C sample into 1000. Unit will be ppm. Okay, so you got the total hardness. Then what is the next step? Fourth step. Permanent hardness we have to find out. How will you find out this permanent hardness? We know that temporary hardness can be removed by boiling. Suppose you boil this solution, all the temporary hardness causing substances will precipitate out. You filter it and remove it away. What is remaining? The permanent hardness causing substances are remaining. Okay, so we have to find out this parameter C boiled. What will we do? Boiled hard water is taken. So first you boil this hard water. Given hard water is boiled, it is cooled. So all the temporary hardness causing substances will precipitate out. Then it is filtered. So what is there in the solution? Only the permanent hardness causing substances are there in the solution. Take a fixed volume of that, mix with ammonia buffer, add the indicator, titrate with EDTA taken in the burette. End point is change of color from wine red to green. Okay, so volume of boiled hard water taken is V boiled. Volume of EDTA required for this titration is V EDTA. C EDTA we already know. So from that we can find out C boiled. C boiled is equal to C EDTA into V EDTA divided by V boiled. And once you get C boiled, permanent hardness is equal to C boiled into 1000. Okay, that much ppm. The unit is ppm. So permanent hardness is C boiled into 1000. So you got temporary hardness, you got you got total hardness, you got permanent hardness. What will be temporary hardness? Subtract that. Temporary hardness is total hardness minus permanent hardness. Okay, temporary hardness will be total hardness minus permanent hardness. So one important question. Describe the principle, procedure and calculation steps involved in estimation of hardness using EDTA 10-mark question. Okay, you can expect this as an essay question. You write everything. You write the principle, the procedure and all the calculation steps. So this is a brief overview of everything. Calculation part. Okay, C standard is equal to W by V, C EDTA is equal to, so each one. So these are the formulas that you have to remember. You may be getting numerical problems from this, so it is based on these formulas. So you have to remember all these formulas. So we have seen how to estimate the hardness, and we have seen other properties of hardness. Now we move on to removal of hardness. So how we can remove hardness from water? Temporary hardness can be removed by boiling, but boiling is not possible on a large scale. Okay, permanent hardness also will not be removed on boiling. So how will we remove hardness from water? So that is called water softening, and this is important in case of the industrial water used in boilers for generating steam. So it becomes very much important. We cannot use any conventional method like boiling, so we have to look for some other methods. One important method is ion exchange. The ions present in water are exchanged for ions which do not cause hardness. So what is done in ion exchange? What is the principle of ion exchange? Cations are exchanged with H plus ion and anions are exchanged with an OH minus ion in an ion exchange resin. We'll explain what is an ion exchange resin. So all the cations in the water are removed, and instead of that H plus ions come into water. All the anions are removed, and instead of that OH minus ion comes into water. So you are getting pure water, pure H2O you will be getting. Ion exchange resins, they are polymers. It is polymer ion exchange resin. Polymers, copolymers of styrene divinyl benzene, they are used as ion exchange resin. So this is styrene and this is divinyl benzene. They will combine together, they will copolymerize and they will form a polymer that can be used as an ion exchange resin. There are two types of ion exchange resins. One is called cation exchange resin, the other is called anion exchange resin. So cation exchange resins, they will take up the cations and they will release H plus ions. Anion exchange resins will take up the anions and release OH minus ions. Now if you look at this diagram, so this is styrene, divinyl benzene, they are combining to do the polymer. So it forms a layered structure, different layers are there, and you can see there is a cross linking between these layers. The divinyl benzene cross links the different layers, and the benzene ring of styrene, that is free, so you can put some functional groups into that ring. These functional groups act as the ion exchange part. Okay, depending on the type of functional group, you will get a cation exchange resin or an anion exchange resin. So cation exchange resin, the functional group can be any of these three: SO3H, sulfonic acid, COOH, carboxylic acid, or OH, phenolic, that is alcohol. Most commonly used functional group is sulfonic acid. So what does this functional group do? You can see in this reaction, the sulfonic acid group present, it will absorb the calcium ions. For example, it will absorb the cations, whatever cation is present, and an equivalent amount of H plus ions are released to water. Similarly, the anion exchange resin, the functional group is this one. This is tetramethyl ammonium hydroxide. Tetramethyl ammonium hydroxide. So this has this OH minus group, and that OH minus group, it will accept an anion and it will go into the solution. So this resin will accept all anions, will absorb all the anions, and it will release OH minus ions instead of that. So finally you have H plus plus OH minus giving water. You get pure water. So this is the working of the resin, polymeric ion exchange resin. This is how it takes place. You have a column. It's a cylindrical tube in which you are filling with the cation exchange resin. Another cylindrical tube you fill with the anion exchange resin. Keep it vertical, and the water, the hard water, is sent into the cation exchange resin. So when it comes out, all cations will be absorbed by this resin and you get cation free water. Then it goes into the anion exchange resin. All anions get absorbed. Instead of that, OH minus ions comes into water, and finally what comes out is pure H2O, neutral pH, pure H2O. This is the working of the polymeric ion exchange process. So here if you see, water is first passed through the cation exchanger and then the anion exchanger. Okay, first the cations are removed, then the anions are removed. Why we cannot follow the reverse? Why can't we remove the anions first and then the cations? Okay, what is the problem there? Like this. Suppose I am allowing the water to pass through the anion exchange and then to the cation exchange. What is the problem? Why can't we do like that? So if you pass water through the anion exchanger, all the anions get exchanged and OH minus ions come into solution. This OH minus ions will react with the metal to form metal hydroxide. Okay, metal hydroxide is formed. Metal hydroxides will precipitate out. Calcium, magnesium, or other heavy ions, heavy metals, hydroxides will precipitate and it will damage the exchange resin. That is why we will follow this method. That is, first we will pass the water to cation exchange resin and then through the anion exchange resin. Advantages and disadvantages of this method. What are the advantages? What are the disadvantages? Advantages: can be used for highly acidic or basic solutions. Any type of solution you can use. produces water of hardness less than 2 ppm. So very soft water you are getting. Disadvantage is that high capital cost. The cost is very high. The cost to set up this whole thing is very high, and turbidity will reduce the process efficiency. Turbidity means presence of colloidal impurities. They will reduce the efficiency of this process. These are the disadvantages. So this question, explain the ion exchange process of softening water. This is a repeatedly asked question for the university exam. Differentiate between cation and anion exchange resins. This is also another probable question for the university exam. Now, we use this ion exchange resin after some time. The ion exchange resin will lose its capacity. Okay, all the H plus ions present in the resin will be exchanged. At that time, this resin will become depleted. Okay, you cannot use it further. Then what will we do? We have to regenerate the ion exchange resin. How do you regenerate? So this is a method for regeneration. The cation exchange resin is regenerated by adding 1 molar acid solution. Hydrochloric acid is used. And the anion exchange resin can be regenerated by passing 1 molar base, sodium hydroxide solution, through it. Okay, so this acid will come, it will pass through this cation exchange resin, and it will come out, it will go to the waste stream. Similarly, the base. So what are the reactions happening when you are passing the acid and the base to this resin? So when the acid is passed, what happens is all this calcium will be replaced by H. H plus will come and sit in the resin. Calcium will go out. Okay. And when the anion exchange resin, when OH minus is passed, the sodium hydroxide is used, this OH minus will come and sit in the resin. A minus, the anion will go into the solution. Okay, so the resin becomes regenerated, you can use it again. Now, next method, that is called desalination. So we were looking at water softening, that is removal of hardness causing substances from water. One method we saw was polymeric ion exchange method. Second method is called desalination. What do you mean by desalination? Removal of salt content from water. Salt can be hardness causing salt, or it can be a salt like sodium chloride or sodium nitrate, which does not cause hardness. Sodium does not cause hardness. Calcium, magnesium or other heavy metals only cause hardness. Sodium, potassium does not cause hardness. But if they are present, that water cannot be used for domestic or other industrial purposes. So they have all cations and all anions have to be removed. Water which contains salt content greater than 1000 ppm is called brackish water. For example, seawater. Seawater is called brackish water. And seawater, how we can make it useful for domestic purpose? The method is reverse osmosis. Okay, reverse osmosis. You are familiar with the term osmosis. Here we are doing the reverse of osmosis. Now let us assume we have two containers. One has, both have the same solution. Okay, like for example, sodium chloride solution. The right container has a concentration more, and the left container the concentration is less. Okay, two different concentrations of the same substance. They are kept together, separated by a semi-permeable membrane. Okay, using a semi-permeable membrane, we are separating them. So what will happen? The semi-permeable membrane prevents all ions from coming out. Only the solvent, water, can pass through that. So what happens here? Water, that is a solvent from the lower concentrated region. A solvent from the lower concentrated region will move to the higher concentrated region. Okay, so from here, this part, the water solvent will move to this part till the concentrations become equal. Till the concentrations become equal. This is called osmosis. You have already studied that. Osmosis. So this is called osmosis, and the pressure that is generated, that is called osmotic pressure, represented as POSM, P osmotic, osmotic pressure. So this is the definition. When two solutions of different concentrations are separated by a membrane, solvent from the lower concentrated liquid flows to the higher concentrated liquid till the concentrations become equal. This is called osmosis. Now we are looking at the opposite of osmosis. You have salt water, you have pure water. This is a semi-permeable membrane. Okay, now you apply a pressure on the salt water region which is greater than the osmotic pressure. What will happen? The solvent from the higher concentrated will go to the lower concentrated side. Okay, solvent from the higher concentrated side will go to the lower concentrated side till the like this. So here the volume or the amount of pure water increases, here it decreases. So we are filtering, sort of a filtering. Okay, suppose this is seawater. Seawater contains lot of salt. The water content of seawater will be separated from the salt content. Okay, this is called reverse osmosis. When you apply a pressure greater than the osmotic pressure, solvent from the higher concentrated region will move to the lower concentrated region. That is called reverse osmosis. So reverse osmosis is a method of purifying or reducing the salt content of saline water. What are the advantages of this method? High lifetime, removes ionic, non-ionic and colloidal impurities. The earlier case in polymeric ion exchange also the same thing will happen. The ions will get exchanged, but their non-ionic and colloidal impurities will interfere, so they cannot be removed. Low capital cost. Comparatively, the capital cost is low. Simple operational procedure. Okay, these are some of the advantages. Disadvantages: complete desalination is not possible. We cannot have 100% removal. Like in polymeric ion exchange, the hardness is reduced to 2 ppm, very low, nearly 100%. But that is not possible here. Membranes are costly. Okay, the membrane, if you want to change the semi-permeable membrane, it might be costly. So these are some of the disadvantages of reverse osmosis. So this is the question. With the help of a neat diagram, outline the reverse osmosis process. Same question. Outline a process by which seawater can be made fit for domestic applications. Okay. Again, what is brackish water? Explain the procedure for converting brackish water into pure water. So reverse osmosis, that's a very important topic as far as your university examination is concerned.